Okay, so let's see. We had a couple things left to do here. So we talked about levers yesterday, right?
Yes.
Okay. So this is what we call a first class lever. That's the one we talked about, right? Where the fulcrum is in the middle. We didn't talk about second class or third class levers though, right? Okay. So this could be, we could either put the fulcrum close to, like this is a trebuchet here, right? Where we're putting the fulcrum close to where we're applying the force, and we can apply lots of force. And so therefore we're trading force for distance, right? The output is gonna have less force, but it's gonna move through greater distances and therefore have greater speed. Okay? So what if we wanted to do something a little different though? What if we wanted to put the fulcrum at one end? So here's the fulcrum, there's the lever, and we're going to put the load in the middle. So the effort's going to be, or the force is going to be out there that we're applying, right? Okay, that's what we call a second class lever. Second class lever has the load in the middle, right? First class lever puts the fulcrum in the middle. Second class lever has the load in the middle. And what do you think a third class lever would be? What's the one thing that hasn't been in the middle yet? The force. Okay, so a third class lever would be something like
a waitress holding onto a tray?
Like that. Yeah, well, yeah, I mean, kind of. Okay, so this would be like a catapult, right?
Oh.
Where it's being the lever is being held rigidly at one end. You're going to put the load at the other end, and you're going to push in the middle with lots of force to get it to swing up apart, right? So it'd be like this. I need like a. Let me grab a meter stick from in here. That would be really helpful.
I know, I get it and
Okay, so this would be an example of a third class lever. Like if I'm pushing right here, see what I'm saying? So here's the projectile right here. And I'm going to hold it down at this end, and I'm going to push, and it throws it, right? You see what I'm saying? So your arm, when you throw a ball, is a class 3 lever. See, because now if you think about it, look, your shoulder is the fulcrum. It's holding your arm in place, right? So it's pivoting about your shoulder. Your muscles are attaching in the middle, and then the ball's up here. The load is up here, right? So see what I'm saying?
Yeah.
Yes, ma'am.
What is the difference between a catapult?
Okay, so trebuchets are better because trebuchets are easier to load with weight. You can load them with more weight because with the trebuchet, the fulcrum is going to be in the middle, like this, right? And so you put the load down there, then you just fill some big basket up or something with weight so you can harness gravity or gravity power. You can use more gravity than you can like elastic energy stored in something. So that's a trebuchet. Well, it didn't work very well, but you get the idea, right?
Yeah.
Okay. Where'd my projectile go?
It's next one.
Oh, right here. Okay. So that's a trebuchet, right? What's an example then? Can you tell me what's an example of teeter-totter would be first class lever or trebuchet or something, right? Or crowbar, okay? What's an example of a class 2 lever? Yeah, what would that be? I mean, it could be a pry bar. It really could be a pry bar. But usually there's a real classic example that will make it easy to remember how this works.
Say it.
So imagine that I'm holding this end of it like so.
Wheelbarrow.
Yeah, wheelbarrow. Yeah.
Oh.
So that's a classic example of a second class lever, right?
And a wheel.
And a wheel. Yeah, and a wheel. How about that? And a wheel too, wheel and axle. So the by the way, in our book does some weird stuff. when you go to college, it'll be different. When you go to college, they'll call it the load and the applied force, most likely, especially if you're doing engineering. But in our book, they call it, here's their notation, it's okay. They say like F sub E equals effort force,
Wait, what is it in real life?
applied force.
Okay.
So that's what you're doing to the machine is the effort force. And then they say F sub R equals resistance force, which is the load. Okay?
Okay.
Right? So then on a wheelbarrow, think how they're built. There's a pretty long effort arm, right? And in our book, they would say D sub E equals effort distance. And we're going to talk a little bit about this. D sub R equals resistance distance. Kind of fun to say. Just try it. It's really a great time. So in this case, we want to put the load as close to the fulcrum as we can so we can pick up heavy stuff. And that's the way wheelbarrows are, aren't they? They've got the bucket is right up over the tire, and then they got the long handles that you pick up from back here, right?
Yeah.
Okay, so let's talk about that a little bit. Did we look at a ramp yesterday at all?
No.
We hadn't really gotten to a ramp yet. Okay, that's fine. So let's look at a ramp for a second then, because a ramp is actually almost an easier. This is really the easiest one in a way to work with. Levers are simple conceptually, but levers it's easier to see the distances. Okay, so a ramp is just an inclined plane is what we call it in physics, right? How does this help you out? How does a ramp help you out? What's it do? I mean, if you're going to be moving, right? If you're going to move your house, you get a moving van, right? How do you get the stuff in the back of the moving van?
Ramp.
You walk it up a ramp. Yeah, you don't pick it up directly. How come?
You're climbing up the wood.
It's too heavy, right? Furniture's heavy, right? So you walk it up a ramp instead. Okay, what's the benefit? Less effort, more distance, right? So if I've got let's say we've got a frictionless ramp here, and I've got a weight at the bottom. If I want to pick that weight up 2 meters, I could pick it up directly 2 meters, right? Or I could slide it up this ramp, which is, let's just say it's 10 meters long. Okay? How is the work going to compare using either method? Equal, right? Equal work. Here I'm applying lots of force through a small distance. Here I'm applying little force through a large distance, right? Everybody see that?
Yeah.
Okay. So how much less force would we apply in this case? What do you think? 1/5, right? Well, you saw it there, but you don't really need to, do you? Right? The work in is just going to be the weight times 2 meters, right? The work out is going to be whatever the applied force is times 10 meters. Well, we know the work has to be the same in as it is out, right? There's no reason it would be any different. Okay? Well, there might be a reason, but we'll talk about that in a second. But it's not going to be to your advantage, it's going to be to your disadvantage. Assuming that this is a frictionless surface and there's no energy lost, then if we solve for F, we find that the applied force, or the effort force, is 1/5 of the weight, right? Okay, so then in physics, we have a name for this. We call this mechanical advantage. What do you think mechanical advantage means? Because you've heard this before. I'm sure you've heard that term before, right? Okay, it's multiplying force. It's putting less force in to get more force out, right? And that's really the critical part of a machine. Most of the time, we're interested in reducing the amount of force we have to apply, right? So mechanical advantage, then, come up with a formula for that. What do you think? What could be a formula for mechanical advantage? How could we predict how much we're going to multiply the force? What? Say it again. Well, okay, sure. I mean, in this case, like the effort force was, let's say this is 100 Newton weight. Okay, so if it's 100 Newton weight, the resistance force is 100 newtons, right? What's the effort force? 100 divided by 5 is 20, right? Does that make sense? So how am I going to come up with a number then from those forces? The mechanical advantage is how much you're effectively multiplying the force. Say it again? Okay, so that's one way maybe we could do this, right? If we want to come up with mechanical advantage, one way maybe we could think about it would just be to use the distances. The other way would be to use the forces, right? Let's start with the forces. How could I set something up? How could I set up an equation involving forces? I'll give you a hint, it's a ratio. What do you think? Nicole, what do you think? What's going to predict how much I multiply the force? In this case, it'd be 20 times 5 is 100, right?
Wait, why?
Well, because we're pushing with 20 newtons,
Oh.
and this weighs 100, right?
Okay.
Okay, so then that multiplies it by 5. So we could say the mechanical advantage is 5, right? We got 5 times more force out. Okay. Okay, so which force divided by which force? Okay, meaning resistance force, right? What they would call resistance force. So F sub R over F sub E, right? That should work, right? Okay, Ryan, you suggested distances. What would the ratio of the distances be? So dr is 2, right? Because we're actually picking the weight up 2 meters. Opposite. It's going to be the reciprocal of that. It's going to be the effort distance, which is 10 meters, divided by the resistance distance, which, the load distance, right? Which is, in this case, 2. Those both should work, right? Yeah. Okay. Yeah, you're thinking ahead here. That's good. Okay. I would argue that only one of those is really going to be useful for calculating the mechanical advantage. The actual mechanical advantage. Which one? The forces. Yeah. How come? Okay, these numbers gave us, they gave us the same answer, which is 5. And they would for every ramp. But what did we omit here? We made this kind of an idealized, we made an idealized situation where we omitted friction, but you never actually omit friction, right? There's always going to be some friction involved, right? So if the friction is actually involved, that's not going to alter the distances at all, right? What's it going to change? Which force? Not the resistance force, because that's just the weight of the object, right? But the effort force. Do you think it's realistic to think that you're only going to have to push with 20 newtons of force to slide that up the ramp? Probably not. That would be if it were absolutely frictionless. There's probably going to be some friction involved, and so what might be more realistic would be something like maybe 40 pounds, right? That make sense? So then, this is the one that's actually predicting, or not predicting, it's actually telling us, what happened, how much mechanical advantage is there in reality, right? So what would it be in this case? It would be 100 newtons divided by 40 newtons of applied force, right? So 100 over 40 would be 2.5, right? The actual mechanical advantage was 2.5. This still might be useful, though. This is the theoretical mechanical advantage, right? This is telling us in the absence of any friction, so with perfect efficiency, that machine would produce a mechanical advantage of 5. Does that make sense?
Yes.
Okay, so in our book's language, they call this one ideal mechanical advantage. Later on in life, it'll probably be called theoretical mechanical advantage. And then this is the actual mechanical advantage, which our book just calls mechanical advantage, right? That's the ratio of F sub R over F sub E, okay? So what do you think then? What do you think is a way we could define maybe the efficiency of a machine? What is the efficiency? Talk to me about the word efficiency. What do you think that means? What's the efficiency of the machine going to be? say how well it works?
Yeah.
Okay, what do you mean by that? You're right.
How much work you put into it?
Oh, okay, so one way of doing it might be to say, okay, how much work are we getting out for the amount of work that we're putting in?
Yeah.
Right? Let's calculate that for our situation here. If this was, we're having to push with 40 newtons, but the actual weight is 100 newtons, well, how much work are we putting into this if we're having to push this 10 meters up the ramp? We have to push with 40 newtons to slide it up the ramp.
What's the angle of the ramp?
Doesn't matter.
Wouldn't it be 2.5?
How do you calculate work?
Oh, is it 400?
400. Elijah, how'd you get that?
Force times distance.
Force times distance, right? Okay, so we know that the input work, we might call this W sub E, is 400 watts? Joules. Okay. What's the output work? What's the machine actually accomplishing? We're picking up a 100 Newton object, 2 meters. No. 200, right? 100 newtons times 2 meters is what we actually accomplished, right? So the resistance work is 200 joules. Oh, so what is the efficiency there? 1/2, right?
What does that mean? Like,
That
it's
means-
1/2 better than.
Well, that means that only 1/2 of the work that we did actually was useful.
But you
The other half of the work was dissipated as we lost the friction.
Right.
So we want 100%.
Ideally, you want 100%, yeah.
Yeah, so how is that useful when you could have just picked up the 100?
Okay, because what if this thing is, there's a couple of reasons. Because,
other than like if it was something.
Maybe you're.
well, there you go, so maybe it's something you couldn't pick up. Maybe the other thing is, it's easier to apply a force along the direction of the ramp than it is to apply a force straight up. So simple machines do really two things. They can change the force profile, right, which is often very useful, but they also can change the direction in which you're applying the force, which sometimes is equally useful.
Kind of like, what is it with pulleys you can pull down?
Exactly, with a pulley you could pull down, you could use your own body weight to raise something up without actually having to do anything, right? Okay. So that's one way to calculate efficiency, would be to take the ratios of the works. What's maybe another way?
How much the actual
Mechanical advantage?
versus how much you could.
Right, okay, so we could maybe say, what is the actual mechanical advantage divided by the theoretical mechanical advantage, right? Because in this case, that would have also worked, right? The actual mechanical advantage was 2.5, but the theoretical mechanical advantage was 5. So we also would have gotten 1/2 out of that, right? Does that make sense? We can relate those pretty easily. I think in a way, well, so let's say we started off with our efficiency equaling mechanical advantage, actual mechanical advantage over ideal mechanical advantage, is what our book calls it, or theoretical mechanical advantage. Well, we can write those in terms of what they are, right? Actual mechanical advantage is F sub R over F sub E. Theoretical mechanical advantage is D sub E over D sub R. If I flip and multiply, look what I get. I get F sub R times D sub R on the top, and F sub E times D sub E on the bottom. Well, that's the definition of what you told me earlier. That's resistance work over effort work, right? And either way, I'm going to get 1/2. How do you suppose we would typically talk about efficiency, though? Would we say 1/2? I think we would do.
Yep.
Probably we'd say 50%. It's 50% efficient. Percentage is an easy way to think about it. What percentage of the work that you're putting in is actually being converted into something useful, right? Okay. All right, so another little point, minor point to make. With ramps, it's really easy to see. It's really easy to see what D sub E and D sub R are. All right. With a lever, not so much. With a lever, technically, this is like if this is a trebuchet, right, where I'm pushing down on this end and I'm picking up the load on that end. then technically, if I move it from here to here, right, I start here and I tip it up like that, this is d sub e, isn't it? Right, that's how far I've applied the force. That's the effort distance. And this would be d sub r. That's how far the resistance or the load has moved. Agreed? That's not always convenient though, right? To have to move it to figure out what those are. So instead, why don't we take advantage of the fact that the triangles, we talked about this yesterday, the triangles that I make are,
Is it not move like in a, we can move it in margin?
what's that?
Wouldn't that D of E be in margin units?
Well, no, because technically it's gonna be how far it moved vertically, because that's the direction in which the force is moving, right? I mean, so really you're taking just a component of it, okay? But
So like the X component doesn't matter, because you're not
Right.
pushing in the X direction.
right. But wouldn't it be easier to take advantage of these similar triangles and instead just use the ratios of the lengths of the arms, because they're gonna be the same thing? You get that, right? That over that is the same as that over that, right? And so we can just by inspection, then we can look at the lever and say, okay, well, how far is it from the fulcrum to the effort? Because that's the effort arm. Just call it d sub e, because really all we care about is the ratio anyway, right? How far is it from the fulcrum to the load or the resistance? That's the length of the resistance arm, but we'll just call it d sub r, because really all we're going to do with that anyway is just calculate probably theoretical mechanical advantage. And the ratio is going to be the same whether we use the blue measurements or the red measurements, right? You see what I'm saying? If we actually want to calculate work, then we really would have to use those distances, though, wouldn't we? Because that's the direction, or that's how far the force is actually moving, right? Okay, so then we could extrapolate this to all of the simple machines, right? So let's just say, for example, that we want to use a wheel and axle. What's a wheel and axle? Well, a wheel and axle is just something like that, right?
That is so good.
Isn't that good? Okay, so then what's that mean? So that means that we're going to either be applying a force here, a twisting force, to twist the wheel, right? Or we're going to be applying a force out here to turn the axle, one or the other, right? Either way, though, think about these. These are really effectively just levers, right? Because if let's just say that we're going to turn this wheel and this wheel's in contact with the ground, right? So the force that's being applied by the wheel to something else is going to maybe be the wheel pushing on the ground, for example, right? And so isn't this distance, the radius of the wheel, really effectively like a lever? See what I'm saying? There's the spokes of the wheel are all levers, but at any one moment, that's the resistance distance, right? You see what I'm saying? Well, what's the effort distance? Well, the effort distance in this case would just be something is turning this axle, right? Maybe there's a chain along the top, or there's a belt that's riding along the top of the axle that's turning it through friction or something, right? And so this is going to be that little distance right there. The radius of the axle is going to be the lever that you're using to turn, right? You're pushing on that lever, maybe with a belt that's riding around the top of the axle or something, right? You're pulling on that belt, and you're applying a force through that big a lever. Agreed? So what do you suppose if the radius of the wheel on this end, let's call this R sub W for the radius of the wheel. Maybe I should color code that. So if this is R sub W, and this little guy down there is R sub A for the radius of the axle, what do you suppose the theoretical mechanical advantage is if I'm twisting the axle?
A fraction
gonna be a fraction what? So in that case, wouldn't this one be the radius? Well, I mean, effort distance, right?
Wait, of the radius with the long axis?
If I'm twisting it here, I'm applying the force here like you would in a car, right? Then that becomes the effort distance, and this becomes the resistance distance, right?
Yeah.
See that? Okay, and so the theoretical mechanical advantage, and usually they call that TMA in other textbooks, right? It's gonna be what? Well, that's always gonna be effort distance over resistance distance, right? So in this case, that would be the radius of the axle divided by the radius of the wheel. It'd be a small number, right? If the axle is, how big is an axle? Say an axle has a radius of, let's just say we use regular, so 2 inches. So that's gonna be like 1 inch divided by the radius of a tire would be probably about, I don't know, 14 inches, something like that. So it's probably about a 1/14 mechanical disadvantage, right?
Wait, why one?
Hey, you
Oh,
know
that you
what
said
that
two.
Say it again.
Why one? Oh, why
that?
one not?
Because we're putting,
Oh,
for
the
every,
diameter was two.
right, for every 14 pounds that of force that we put in, or 14 newtons that the engine produces, it's only producing 1 newton of force on the ground, right? Okay, why is that? Well, the engine can produce lots of force, right? But what we're trying to do here is trade all that force that that big engine can produce for extra distance or speed.
And that doesn't do that thing, right?
Well, it does, because the engine, we're providing a whole bunch of force to turn this thing, but every time I turn it once, that wheel goes to a pretty big distance, the tire does, right? Okay? In a car, you can actually change that ratio effectively, though, if you look inside the gearbox, right? Because the gearbox is doing the same thing, right? Inside the gearbox, there's gonna be a series of gears in the car where the engine's gonna be turning, like it's gonna be turning, for example, let's just say that this is the gear being turned by the engine. It's got teeth on the outside. I'm making this kind of simple. And let's say this is gonna be the gear that's attached to the axle of the car. So let's say it's a chain drive car, which there actually are chain drive cars. So there's the chain, right? Well, that's a wheel and axle also, isn't it? Because now here's, in this case, this would be R sub E, and this would be, well, I guess D sub E, and this would be D sub R, right? And so in the transmission of a car, you can change that ratio, right? You can shift gears. See what I'm saying? So by changing the relative sizes of the wheel and the axle, right, inside the gearbox, you can make it easier or harder for the car to, you can change the mechanical disadvantage, right? Does that make sense? So when you're first starting off, you're gonna wanna have a mechanical disadvantage that's gonna be relatively small, because you wanna be able to apply lots of force to get the car moving, right? Does that make sense? Or if you want a steep hill, for example. But later on, when you get up, you wanna go faster, so then you've gotta make that mechanical disadvantage smaller so that you can get more speed out of it. See what I'm saying? Right? You get the idea? So all this stuff we're talking about, it's the same, each one of these simple machines is just a different way of manifesting the same equation, right? Mechanical advantage is mechanical advantage, right? Just depends on, it's just kind of, this is a wheel compared to an actual lever, but you get the idea, right? If you were to, what about this one? What if we want to split a piece of wood and we use a splitting wedge, right? We put a metal wedge in the wood and we hit it with a hammer. What is that really?
Axe.
Well, it could be an axe. I mean, an axe, it could be an axe or it could be a separate splitting wedge that you're hitting with a hammer or something too, or a maul. But what kind of simple machine is that? Okay, yeah, a wedge is technically just an inclined plane, is really what it is, right? Does that make sense?
No.
I mean, if you think about what you're doing with our ramp, if I go back a little bit, where's that picture? Right. Oh, that's way too far back. So that looks like a wedge, right?
Yeah.
So look what happened here, right? We only had to apply 40 newtons of force along the wedge to produce 100 newtons of force vertically, right? Okay, so now let's reverse that. Now we're going to hit the wedge from this side, right? So when we hit the wedge from this side, we're going to slide the wedge down into the wood, right? Well, with how much force? Well, maybe it only takes, 40 newtons of force to slide the wedge into the wood, but I'm getting back 100 newtons of spreading force.
Okay.
You see what I'm saying? Right? Okay, and so why is that so useful? For a couple reasons. It's so useful because you multiply the force a little bit, sure, but then also, probably more important than that, it redirects the force, right? It's convenient if you're splitting a log. It's easy to swing something down onto the log and produce really large forces, right?
Yeah.
But how are you going to get that force shifted so it's pushing the log apart?
The wedge.
With a wedge, simple machine.
A hammer.
Okay?
A hammer.
With a hammer, yeah. Otherwise, it'd be pretty hard to do that, to just pull that thing apart.
I could do it.
Knives is the same thing, right? If you're cutting a
Yeah.
tomato with a knife, all that is an inclined plane,
Whoa.
right? You're just pushing down with the
Just a
minimal amount of
sharp
force,
incline.
and it's sharp, so it's a really, really, if you look at a knife in profile,
Oh.
a knife would be a wedge that would look like
Oh, pressure.
that, right?
Yeah.
The knife is hugely multiplying the forces, right? Because look at the ratio here. You got a big distance divided by a small distance. That's a really big mechanical advantage, right? So a little bit of downward force produces a lot of separating force, right?
Yeah.
Make sense?
With pressure.
Yes. And there is something else going on there too. There's the high pressure, but we'll get to that later. I have one more, and then we got it all covered. If you look at a screw is really just an inclined plane also, right? A screw is equivalent to doing this. It's equivalent to taking an inclined plane.
How is screws
Yeah.
helping your? Oh yeah.
And then what I'm gonna do is I'm gonna try to wrap that around this core, right? So I've got this. Here's the screw, and I'm just gonna wind it up around that thing as it goes, right? We don't really need the bottom of it anymore. All we need is just that groove, right? And so as I wind this thing up, I just end up getting in profile, I just get something that goes around and around, and that ramp just gets twisted around and around and around the core of the screw, right? So that's really all I'm doing though. When I drive a screw into wood, I'm able to, I've got a really long ramp wound up around that core, and so I turn that ramp through big distances in order to apply a very small force to a large distance to apply a very large force into the wood.
Yeah. Because if you do like just a straight like needle and then put it through wood, would it be not as good as like screwing a screw?
It wouldn't, right? If you use like a nail is more
Yeah.
like a wedge,
Yeah.
right? A nail is a different kind of an inclined plane, and what's holding the nail in place is just friction, right? That's all it is.
Is a screw better than a nail?
I mean, there's yes and no. I would say almost always yes, because you can remove them for one thing. Yeah, it does. It really does. Yeah, a galvanized nail sticks pretty well. It really does.
Do you think there's any simple machines we haven't discovered yet?
Yeah.
Well, I mean, no. There might be different manifestations of the simple machines that we have, but not really. I mean, they're all the same thing, really.
That's what I mean, it seems like so far you've either said they're either a lever or an inclined plane.
Yeah, that's really, I mean, and I guess you could say a wheel is separate, but it's really not. I mean, it's really just a
That's what I'm saying,
lever
it's
that's
like,
spread out
is
over a whole.
Is it really
No, I don't think they're.
Pulley with a pulley.
Okay, what about pulleys? Good thing you asked. What about a pulley? So here's like a block and tackle. We have a pulley system. Let's just look at a really simple one. Let's say that we've got, okay, here's a pulley. So I'm gonna pull on this end of the rope, and it's gonna be attached to a weight.
Oh yeah.
Okay? Assuming a really good quality frictionless pulley. which is impossible, but if you spend a lot of money, you can get a pretty low friction, high efficiency pulley. Okay. So if this weighs 1,000 newtons, how hard do I have to pull down to pick that thing up? 1,000 newtons.
Oh.
Exactly, right? Because think about this. What does the pulley do? The pulley just turns this situation where you're standing out here holding this rope down here that's attached to the weight, and you're picking it up. Obviously, that's 1,000 newtons, right?
Yeah.
What did the pulley do? All the pulley did was it just bent that around something so you could more conveniently pull from the bottom. Right? Make sense? So that's the tension in the line is 1,000 newtons, either way, right? But this is different. Watch this one. What if we do something tricky with this? What if we say, okay, now we're going to go, we're going to do this. We're going to go. Okay, so that one's hanging from the ceiling, and this is attached to the ceiling, let's say, right? And this
Oh, but
pulley
also
right
the
here
pulley
is
will
attached to the box that you're picking up. Okay, so the box is 100 newtons, right? How hard do I have to pull to pick it up this time?
50.
50. It is 50. You're right. What's the tension in the rope? 50, right? What is the tension? In order to support this thing, how much force has to be directed upward if this weighs 100 newtons? 100, right? But look, there's two segments of rope that are pulling upward, right? So let's just ignore this part for a second. Doesn't that mean that I just have to be able to pull up this way? What? Pull up this way with 50 newtons and that way with 50 newtons to support the 100? Each segment of rope pulls up with 50 newtons? Well, that's just the tension in the rope then, right? That means all I have to do is pull down with 50 newtons. I have to put 50 newtons of tension in the line, and it's going to be doubled. But what's the trade-off going to be? I'm going to have to pull this rope down 2 feet to raise this up 1 foot.
And it's right, you get it to 4 or 3.
Oh, I see.
So,
You only do 2 for pulling.
no, so you could do a whole, I mean, you could make this more efficient though, right? I mean, you could make this a bigger mechanical advantage. What if I stacked up a whole bunch of these in a row? So it went down and up and down and up and down and up and down and up and then ended over there, right? You could easily do that. And you've probably seen situations like that where people are pulling, like you're picking up an engine out of a car. You're using a block and tackle and the chain goes over a whole bunch of pulleys, right? So how would you calculate the theoretical mechanical advantage of a pulley system, I suppose? Otherwise, doing the block and tackle. That's it. All you gotta do is you just have to count the number of segments supporting the load, and obviously you're only pulling on one, right? And so the ratio of, of the number of segments supporting the load to the one segment you're pulling on, in other words, the number, that's just divided by one, it's just the number, right? So the number of segments supporting the load determines what the theoretical mechanical advantage is.
Wait, aren't pulleys also involving wheels and axles?
Well, okay, they are. You're right, they are. But in each of these pulleys, it doesn't really matter what the radius is of any of these pulleys,
Okay.
right? Because you're pulling on this side and the load is pulling on that side, and the arms are going to be the same length. See what I'm saying?
Yeah.
You're both pulling on the same wheel, right? Now you could combine the two. You could have a pulley system where you're pulling on smaller pulleys and then it's turning in a wheel and axle which is pulling a bigger pulley, for example. I mean, you could combine the two, right? Usually you don't though. Usually you just have like to combine them, you would maybe have a machine down here that's like you would have maybe a winch, which is just a wheel and axle system driving a pulley. Okay? Does that make sense?
Yeah.
Okay? That's simple machines. That's chapter 10. We're done. About that.
Wow. Yeah, no test or assignment, just learn.
Just learn.